Astronomers celebrates the spirit of discovery and is made possible by the W.M. Keck Foundation, advancing the frontiers of education, science, and medical research. The W.M. Keck Foundation, investing in excellence.
Leonid Grishuk, theorist, on a road into an unexplored realm of astronomy.
The gravity-based astronomy is a very fascinating subject, but maybe the most interesting thing is that we cannot even imagine the kind of new events, the kind of new phenomena which we can discover.
Great ideas need time to unfold, so a theorist's first priority is time. Time to think.
I sold my car. I found myself a slave of my own car. Instead of looking carefully on the road and be always concentrated in order not to hit the previous car, now you rely completely on the bus driver and continue your thinking, your scientific research.
But this can take a personal toll.
I just don't remember the details of my life. I better remember everything in my life if I can immediately relate it with my particular publication or with my travel somewhere abroad. Then I can establish some order in the things around. Sometimes I don't remember exactly what is the birthday of my children. It is shame.
Leonid Grishuk, his wife Tanya, and their 21-year-old daughter Katya often visit his in-laws' dacha outside Moscow. It's a chance for them to reconnect.
I'm afraid they are not happy, because living with a theorist, it is an entire mess.
A gravity wave theorist is a lone wolf. Grishuk spends most of his waking hours theorizing about concepts still to be verified by direct observation.
Theorists normally are not prepared for getting food, for helping wife and daughter in their home. So I think they would prefer to live with someone who can do more with his hands, not with his brain. Well, sometimes I think I am of a great help for them, not always. Well, I have some duties, it is true. The most primitive work is the one which they allow me to do, like bringing some water, going down to buy some potatoes, and to earn money. So, if something happened, like you need to break your entrance door because your key is lost, then you need to do some more sophisticated work. I think this is a kind of work for a theoretician.
Но я его никогда не воспринимала как теоретика.
She never accepted him as a theoretician. How did you accept him? Do I help you?
Yes.
Yeah. Do you think that I am not just a pure theoretician, that I can help and do I earn money? Yeah. Answer in English.
редко бывает дома, редко проводит время с семьей. Но я уже к этому привыкла.
Зато home, spends too little time with his family, but sometimes we spend time together, right? Would you prefer him to change?
Ой, наверное, уже нет. Я к такому привыкла уже.
She has accustomed to this one. She do not want to change him. But as you particularly, as you are concerned, do you think that it is very bad to be a member of a family of theoreticians?
He does not feel himself as an ordinary person.
Oh, that is not true. It is
Like
not true.
as his family.
No, it is not true.
It is not
I deny. I think
it is my own opinion.
Opinion? How can you confirm your opinion? Well, do you have any confirmation of this?
Confirmation, what a theorist always seeks.
It is very interesting because I always consider myself as an absolutely ordinary, absolutely average person.
For 20 years, Leonid Grishuk has been thinking about a new way to observe the universe. Gravity waves. Gravity waves are ripples in space that arise from exploding stars and other violent events.
Gravity waves are very different from other types of radiation and particles. It is like a new kind of feelings. I know that there is a famous song, its name is New Kind of Feeling. So if I'm going to explain what will we have while detecting gravitational waves, it is like we will have new kind of feeling.
Gravity waves could even tell us how the universe began. Grishuk's major contribution has been to realize how gravity waves produced in the moments of creation might have been amplified as the universe expanded. He calls these waves relic gravitational waves.
Personally, I think that they promise us the most important astrophysical information. Relic gravitational waves means that they are left for us from the very, very early stages of evolution of our universe. It may be the only way for us to learn something about the early universe.
The early universe. Astronomers, physicists, mathematicians all converge in the search for clues to the first moments of creation. Some scientists see the universe through telescopes, while others see it with their minds. But who's to say which sees the farthest or probes more deeply? Kip Thorne, another gravity wave theorist, returns to Caltech in Pasadena after a month's absence.
Hi, Pat.
Oh, hello, stranger. Welcome home.
Well, thank you, I guess.
Here's your schedule for today.
Oh, gosh.
And 9:45, you have Joel Peterson, who wants to talk to you about the Moscow meeting.
It's a new one. Hi. You're Joel Peterson?
Yeah.
I'm Kip Thorne. Hi. Listen, I'll be in a little bit. I've been out of town for a month, and they have moved my office bodily.
Keeping up with Kip Thorne is no easy matter. PhD from Princeton in 3 years. Caltech tenured professor at age 28. Black holes, gravity waves, the nature of time.
Well, let's get one more chair in here and try talking here. So
The outer edges of science are Thorne's domain. He's in demand.
Let's see, I guess we're now just missing Amos. I'll be in about 5 minutes, okay?
We have a question, as
Obviously.
a matter of fact.
Yeah.
Do you need a slide projector?
Do I need it?
Well, you are going to talk. You don't know that
I didn't
yet.
know I was going to talk. I thought we agreed I wasn't going to talk.
You are going
We
to talk.
agree that you are.
Thorne is searching for plaques that record scientific bets he's made. Gravity waves are a popular wager.
I made a bet with Jerry Ostreicher of Princeton University about when gravitational waves will be discovered. Now, Jerry is one of the more conservative people around, and so he bet that gravitational waves will not be discovered until after the end of this millennium. Haha, found them. Eureka. His wager was one case of good French wine against my one case of good California wine, that they will be discovered by the year 2000. Of course, we know which kind of wine is better, and I think I know who's going to win. There we go. There's Stephen Hawking. I'm told that he has signed off on that bet, and he's going to send me my reward. That he admits black holes do exist in Cygnus X1, or there is one there. But I have yet to see my reward. Bruno Bertotti hereby bets Kip Thorne that no gravitational waves will be discovered before midnight of 1988, May 5. Except for waves detected by the solar probe, which is a mission that has not occurred yet. The prize will be a dinner paid by the loser, me, for the winner, Bertotti. The loser will attend the dinner.
It was Albert Einstein who first predicted gravity waves, but he thought they might be so weak as to be undetectable. Einstein's greatest work, his theory of relativity, deals with gravity. Einstein proposed abandoning the familiar picture of gravity as a force acting between objects. The better way to think of gravity, Einstein said, is as a bending of space itself.
Einstein had this marvelous new view of gravity as being a curvature of space and time, or curvature of space-time, as we say. Well, if you go back much longer ago than Einstein, Isaac Newton in the late 17th century gave us the vision of gravity, the understanding of gravity that we're most of us accustomed to, where you say that you have two objects, that any two objects like my fist and this can, they attract each other with a force of gravity, and they pull each other together. The Earth and the Moon pull each other together, the Sun and the Earth pull on each other. Einstein realized around 1905, 1907, that there was a fundamental incompatibility between Newton's laws of gravity and the laws of the behavior of matter and of motion. Finally, in 1915, he came to a very deep understanding of gravity. That's his general theory of relativity, where gravity is not thought of as due to an attraction between my fist and the can, but rather that my fist creates a bit of a curvature of space and time in its vicinity. The can feels that curvature of space and time in its vicinity, and that curvature then draws the can into a motion, a falling motion, so it falls toward my fist, sort of sliding down the curvature of space and time between. And similarly, the can creates a curvature of space and time in its vicinity, and my fist feels that, senses that curvature, and it goes sliding down that curvature toward the can. And this is what gives rise to that, what we think of as an attractive force.
According to Einstein, every object causes a bending in the fabric of space. Einstein also realized that this bending of space could produce waves. He saw that if two objects move around each other in orbit, they will create ripples in the curvature of space. Ripples which expand throughout the universe, carrying clues about their origin.
And that's what a gravity wave is. And in fact, Einstein's general relativity demands that there are ripples in curvature of space and time that do propagate, come to Earth and bring information to us from some distant cataclysmic event.
For instance, gravity waves from an exploding star could tell us how the star exploded. Most theorists doubted that these faint waves could be detected, but the first experiments changed Thorne's mind.
Gravitational waves were an entirely theoretical subject up until the time that Joe Weber started attempting to detect gravitational radiation.
In 1964, the pioneering Weber designed and built the first gravity wave detector. He hung an aluminum bar and monitored it with incredible precision, seeking the tiny motions that gravity waves would cause.
As a result of Weber's work, I became strongly convinced that gravitational wave detection was likely to have real payoff and provide us with a new window onto the universe, possibly revolution in our understanding of the universe. I became convinced of this primarily through long conversations with Vladimir Braginsky, one of my closest friends. And we would meet in Moscow, and I became more and more convinced through these discussions that this was a field that was really going to succeed experimentally. I was in that period playing the role of the house theorist in some sense for the Moscow group because Leonid Grishchuk had not yet at that time gotten involved. He has since and has sort of taken over the house theorist job for me in Moscow.
Come in.
Hi.
Have some tea and listen.
Okay, I like your tea. Thank you.
Volodya Braginsky, Volodya is short for Vladimir, and Leonid Grishchuk, Leonid is short for Leonid, are two of my closest friends. I've worked with both of them for a number of years on joint scientific research.
Volodya is an experimentalist. He always, everything feels by his heart. My impression is...
By my liver.
Yes.
My liver is wiser than my heart.
Yes.
And is wiser than his brain.
Yes, it's quite possible. But I never understand him from the first conversation. I never understand what he means. Because for me, it is very, very unclear set of ideas. He goes back and forth. But suddenly you start understanding that there is something behind. Something worries him. Something does not take him chance to sleep quietly. And only after a while you start formulating this, improving, disproving some of his previous claims, and after a while you see that his initial intuition was correct after all.
Leonid is almost as excellent as Kip is. Kip is stronger.
Braginsky, Volodya, even has in his office a desk that he claims is mine. He got it from the Soviet bureaucracy by saying he had to have something for Thorne whenever Thorne visits. But actually, I suspect he wanted it for himself.
Oh, this is Kip Thorne desk. It's not mine. But when Kip is out, I used to sit down here.
Braginsky's colleagues around the world agree that his exceptional inventiveness more than compensates for limited technical resources in the Soviet Union. He was Thorne's natural choice to lead Caltech out of the theoretical into the experimental stage of gravity wave detection.
But Braginsky made it clear that he did not want to leave the Soviet Union. The other person that we thought about very seriously and finally settled on was Ron Drever. We stole him from Glasgow, Scotland. At the same time, Ray Weiss at MIT was developing a new type of gravitational wave detector, a type that Drever was just switching over to and putting new twists of his own onto. And so by 1980, there were two research groups in the United States, one at Caltech and one at MIT, working in parallel on development of gravity wave detectors. In 1983, a marriage was made between our two groups, and for a while thereafter, the groups were jointly led by a troika of Ron Drever, Ray Weiss, and me. We call our joint project LIGO, which means Laser Interferometer Gravitational Wave Observatory.
Caltech's prototype gravity wave detector fills an entire building. Its principal designer is Ron Drever.
Imagine a gravity wave coming down from a source in the sky. At one instant in time, it has the effect of pulling out space, say in this direction, and at the same time squeezing in space in a direction at right angles. And we can observe that if we have suspended bodies that can move in response to the motion of the space. And we have one of these here, another one 40 meters away in a vacuum tank down at the end of the hall. We have another one here, another one 40 meters down in that direction. So what we have to do is to measure very precisely the distance between these two and compare it with the distance between these two, and there should be a difference when the gravity wave goes past.
A gravity wave would cause one arm to shrink while the other arm stretches, but the movements would be extraordinarily small, far less than the size of an atom. Lasers offer a way to make the measurements work. The technique involves splitting the laser beam into two. MIT's Ray Weiss.
The essential components of it are a beam splitter, which is a device which reflects light as well as transmits it, very much like what you see when you look into a window pane yourself, and you see your own reflection, but you also see the outside world. And then two mirrors, which are drawn this way so one can see the paths in the interferometer. And then light, green light, is brought into the interferometer. And at the beam splitter, it splits into one beam that goes up and then goes through the mirror and comes back again. And the other beam that encountered the beam splitter goes to the other mirror on the right here, does its path, and comes back to the beam splitter. Now, when the two beams come to the beam splitter after they've passed through the system, they are waves, and one wave, if the mirror's in the right position, will be going up and down, and the other one will be going down and up. It'll look something like this. And so let me draw a picture of that. Let's say the beam that went to the right is doing this and this, while the one that went up is doing this and that. And if they adjust this just right, the two beams will add together in such a way that they give you nothing. In other words, it'll be dark here because these two things cancel each other. And under those circumstances, we see nothing.
But nothing occurs only when the two beams are perfectly aligned. A gravity wave would disturb the system, and the laser light would flicker. However, gravity waves are so weak that this prototype detector cannot really hope to find them. For that, Caltech and MIT are planning to build LIGO, the Laser Interferometer Gravity Wave Observatory. LIGO's arms will span 2.5 miles in each direction. If congressional funding for this $200 million project is approved, 2 LIGOs will be built, one on either coast. The team hopes to have LIGO operational by the mid-1990s.
Now, gravity wave detectors aren't like telescopes because they don't point at a star particularly. In fact, a gravitational wave interferometer can detect signals from almost all directions. But the idea is that if we have a number of these around the world, then in combination you can work it out. Because, say, a gravity wave traveling in this direction at the speed of light is going to arrive at some of these ones first, a little bit later, a few milliseconds later, it'll reach the other ones. By very precise timing, over a number of places like this around the world, you can work out where the wave came from. It has another very special property that you can't do with other telescopes. This telescope looks at the same time in all directions, because gravity waves will go right through the world. Nothing stops them. They go right through the world. They could come right through this side and be detected on this side here. So in a sense, this worldwide network of gravity wave detectors is like a huge telescope, the size of the world.
Leonid Grishuk shares Ron Drever's dream. He looks forward to the day when the Soviet Union will join that international effort. The search for gravity waves leads to remote places, closer to Baghdad than Moscow. To reach this valley in the Caucasus Mountains between the Black and Caspian Seas, Grishuk flies 3 hours from Moscow, then drives another 3. His destination is a tunnel which bores for miles straight into the belly of the mountain. Inside, the Soviet prototype of a gravity wave detector shares space with a major facility for detecting neutrinos. Once as elusive as gravity waves, neutrinos are now detected routinely. Neutrino astronomy has become big science. But gravity wave detectors do not yet command major funds, and for now, space for the modest prototype must be borrowed.
We are in the tunnel of the neutrino observatory, and it is supposed to be not only neutrino observatory, but also the place where our gravity wave detector is located. So here you see our laser.
For Grishuk, these meager facilities are frustrating. They do not begin to match the sophistication of Soviet theoretical work.
I feel sad because I realize how far behind of our colleagues from the United States and other countries we are presently. And although from theoretical point of view everything seems to be so clear, I can explain all of these astrophysical events, but it would be nice to see this detected, to see when gravity wave astronomy is really working for exploring nature. My astronomical career started from reading a book. I even remember the title of this book. It was Birth of Worlds. Very close to what I'm actually doing now. When I was about 14 or 15, I built a small telescope and spent quite a long time observing stars and planets. At some stage, I remember that I was very puzzled by the title of one book. It was matter, space-time, and gravity. I realized that all these notions are united somehow. So as a result, I betrayed my telescope for theory. Well, I never promised my telescope to be faithful to it, so I cannot say that I betrayed it. Kip is a great physicist and a great person. He is a friend of mine. Observing other people, I could see the most deepest parts in their personality. So in the case of Kip, I did not reach his bottom yet.
I crave working in a situation where I know that if I don't do it today, it's not going to be done tomorrow by somebody else. I suppose I'm somewhat like the Daniel Boone that I read about when I was a boy. Daniel Boone, who wanted to move on when he saw the smoke of another settler's cabin fire rising above the hill on the horizon. It was getting too crowded for him, and it was time to move someplace where he couldn't see his neighbors. I'm not really that extreme, but having 100 others around the world working on identically the same thing, I hate that kind of a way of working, and Leonia thrives on it.
He loves to work in a field where there are lots of other people working. He thrives on the competition, on the teamwork. He's a sportsman in science, as in soccer.
At Moscow State University, the Sternberg Institute for Astronomical Studies is a major astronomy center. But the institute, like much of Russia, has little modern equipment. For example, only 2 powerful desktop computers for 200 scientists. Today, with an arrival from the West, the ratio will improve.
Oh, it's one computer!
first came to Caltech, they offered me a job as a professor. And after they offered me the job and I accepted, they asked me then, are you an astronomer or are you a physicist? What kind of a professor do you want to be? And I thought for a little while and decided, since I'd never taken a course in astronomy in my life, even though I was doing research in astronomy at the time, I'd better not be an astronomer. So I told them I'm a physicist. It was a good thing, since nowadays I spend maybe a third of my time doing things related to astronomy, but most of the time these days I sit back in physics. Hello. My wife Carol Lee and I have been living apart for these last 2 years because of her work at the University of Wisconsin and mine at Caltech here in Pasadena. You say you're coming back on the 2nd. Our lives have been a series of phone calls and of trying to match calendars so we can get together for a few days whenever possible. You want to make a little bet? We'll hang it on the wall at Caltech. Okay. Right now she's at a conference in Phoenix, and then she'll meet me at Los Angeles Airport and we'll head off to Oregon together.
Of course I'm picking you up tomorrow. I wouldn't miss it for the world. I haven't seen you in a month, and I'm not going to see you for another month. Well, you may have to wait for me. I've got this Caltech thing running probably until about 6 or 5:45, and I'll make a beeline for the airport as fast as I can. But if I don't get there...
Millisecond pulsars are essentially recycled neutron stars that are spun up to periods of about a millisecond to 100 milliseconds. So even though the periods can be 100 milliseconds, they're still called millisecond pulsars.
You just have to wait at the gate.
Megaflops comes in because the analysis for this was done on a concurrent...
You know, my grandfather, my mother's father, told me when I was a small child that I would have failed in life if I didn't find a profession when I grew up that I loved, so that work was like playing. I took that to heart. I remember him telling me a number of times, and that's what I've found, and it probably contributes to the peace of mind I have. I can't do creative work unless I have peace of mind. There's always a little bit of, in my case, competition with myself. I got more public attention than I deserved early on in my career, and you know, I find myself always seeing whether I can achieve in terms of science anything that remotely approaches the amount of public notoriety I've gotten. And so there's that bit of internal tension with regard to my career, but that's about the only thing. Other than that, I just simply enjoy life.
Thorne, who successfully pursues the unfathomable through the corridors of the universe, can't find Gate 1.
Gate 1. Where the hell is Gate 1? Gate 1's over there. There you are.
Are you You really lose me.
I lost you. Oh, God. I come up here to Oregon to be able to think, to write, to do creative work. It's impossible for me to do any creative work unless I have large blocks of time. And I can't do that in Pasadena because there are always problems arise at Caltech that I need to deal with, if not today, then tomorrow. So to have a place like this where I can be secluded in a way and they know that I'm not readily available is essential for creative work. Walking by the beach, I've had some of my best ideas. I never get tired of looking at the ocean. In a way, you can compare ocean waves to gravity waves in space. Just as ocean waves are undulations in the surface of water, so gravitational waves are undulations in the curvature of space. And just as ocean waves come in all heights, ranging from a small fraction of an inch to many feet high, similarly gravitational waves should come in a wide variety of heights. The problem in detecting gravitational waves is we don't know how high the highest ones are. When you think of waves that are a small fraction of the diameter of the nucleus of an atom, you can understand how difficult it is to detect these things. Now, just as ocean waves come in a variety of wavelengths, similarly gravitational waves should come in a variety of wavelengths, of distances between the crests.
Gravity waves come not only in different heights and wavelengths, but also in various shapes called waveforms. These waveforms arise from different types of events in space.
And in fact, by looking in detail at the waveform, one should be able to decipher the details of what the source was and what it was doing. For example, if you have two black holes that are going around each other, they spiral together, whirl real fast and coalesce to form a single black hole, you'll get a unique waveform that will jiggle back and forth faster and faster, and then you'll get a dying out jiggle. If you looked at some other kinds of gravitational waves, you may have a very different kind of a waveform. There may be a waveform that just goes bloop. And that kind of a waveform could be produced in a supernova explosion, for example. And so if one goes out with a gravity wave detector and sees the bloop waveform coming in, one infers first that, yes, that was a supernova explosion, but also with a network of several gravitational wave detectors, one can infer just where on the sky the supernova explosion occurred. And one can then go out and immediately notify by telephone observational astronomers at the large optical telescopes and say, there was a supernova explosion right in this particular region of the sky. You should go train your telescopes on it and watch for it, because you'll see the light becoming very bright there within the next several hours. The point is that the gravitational waves come out immediately, but the brightening of the light in a supernova will occur only after an hour or two later on. So there is time to notify your optical colleagues to go look. And so far as I'm concerned, that is the real meat of this business, is to turn gravitational wave detectors into a tool for astronomy, for probing the universe, and for learning the detailed behaviors of great, huge masses, black hole collisions, supernova cores, and so forth. Much understanding of how gravity waves behave and how they're produced has come from research done by my students. Regardless of where I am in the world, I still work with my students at least once a week. If I'm not in Pasadena, I talk to them one after another by speakerphone, and we discuss each student's research. Now, let's begin with you, Fernando.
Tell me what you've been doing the past week.
Teaching students how to do research follows the time-honored tradition of apprentices working hand in hand with master craftsmen. Give me brilliant and creative students, and I'll set them moving in a direction such that they do such great work that it will often eclipse my own.
In Moscow, Grishuk works with his students on the subject that most fascinates him, the gravity waves produced in the Big Bang. Like Thorne's students, Grishuks sometimes find things their professor missed. 3 of them have found a stumbling block that may hinder detection of Grishuk's cherished waves, a stumbling block Thorne thinks may be major.
Leonia and I have some disagreement about the prospects for detecting relic gravitons, gravitational waves from the Big Bang. Leonia and I agree that the best way to go after these relic gravitons is by means of gravitational wave detectors flown in space. However, as Leonia's own students, Lipanov, Postnov, and Prokhorov have shown, there is likely to be a background of waves produced by another source, binary stars, where 2 stars orbit around each other. And those waves are likely to cover up the relic gravitons that are so important to Leonia and me. The question is whether there is some region of frequencies, probably at the high frequency end, where the waves oscillate real fast, where the waves from binary stars will become much weaker and the relic gravitons will stick up above them. Leonia is quite optimistic that that'll be the case. I think it's going to be nip and tuck.
But Thorne and Grishuk agree that the most promising way to detect faint gravity waves from the Big Bang will be to build a system like LIGO in space. A system on Earth would suffer too much from vibrations in the Earth itself. A LIGO system in space would be a technological high-wire act, using laser beams that reflect along paths 6 million miles long. But a space-based LIGO lies decades in the future. It is the only type of experiment yet conceived that could probe the very earliest moments of creation, earlier than a billionth of a trillionth of a second. Theorists who seek to understand this era must unite the vastness of astronomy with the minuteness of particle physics.
Astronomy, in some sense, is a branch of physics. So a branch of physics that deals with what we see through telescopes. And it all comes together in the basic issue of the nature of space and time.
There was some time where there was no time. There was no even notion of time. So you can go back in time and suddenly you can discover that you cannot assign any meaningful concept to the notion of time. It was so different physical universe that the very notions of time and space did not exist.
I'm trying to get into some of these deep issues, which are very far from ordinary experience, but for which we have strong hints about in our attempts to understand the origin of the universe.
This is a world where normal laws don't apply, an almost incomprehensible world that can be explored only in the mind.
Sometimes I talk about the early universe as if it hasn't happened yet, because I, like other theoretical physicists, spend much of my time behaving as though I were God, in the sense that we have our own theoretical model universes that we play with that approximate our own universe. And we think in terms of turning the universe on and watching it expand, or turning the laws of physics on and watching them develop. A holy grail for theoretical physics is to understand the creation of the universe. We have 2 great bodies of physical law, Einstein's laws of curved space and the laws of quantum mechanics, and by marrying them to each other, we hope to understand the very creation. These 2 sets of laws are like water and soil. When you mesh water with soil or with sand, you can sometimes get quicksand, which sucks you into it in a way that neither water nor soil can do. In the same way, if you merge curved space with quantum mechanics, you'll get a new set of physical laws, the laws of quantum cosmology, which govern the very beginning of the universe. The laws that determined the other laws that came out of the beginning of the universe, determined the particles that came out of the beginning of the universe, determined ultimately the birth of galaxies, the solar system, and us.
Mr. Ernst Schlegel-Höfer
The few scientists who grapple with deep questions of quantum cosmology are scattered throughout the world.
British Airways desk.
In terms of quantum cosmology, my favorite field, I think that Cambridge School is the most close to my way of thinking. So for me it was always important to go to Cambridge to talk to people like Stephen Hawking, Gary Gibbons or Malcolm Perry.
Malcolm Perry is a member of a group of theoreticians led by the well-known physicist Stephen Hawking. Grishuk has come to interact with this group.
Coordinates don't lie on the real line, but are in some sense constrained to lie on some other manifold.
To physicists, interaction has both a technical and a people meaning. Technically, interaction occurs when tiny particles collide, sometimes forming new kinds of particles.
It's not of eigenstate of...
On a personal level, interaction means a mental collision, one that may yield new intellectual fruit.
Negative.
You know, you started too technically. I mean, can you please repeat? So I didn't understand.
If the variables live on the whole real line...
But in science, each subfield has become so specialized that it may take 2 or 3 days, a week, for scientists to explain their work well enough for colleagues to understand. Only then can they ask meaningful questions or offer contributions.
If they live on a circle, it's actually rather hard.
Since the 17th century, Cambridge University has been a center of theoretical physics in England. Newton walked these streets, working out the basic theory of gravity, which Einstein's theory superseded 2 centuries later.
Is I times A, and crudely speaking, pi is the same thing as IA d by dA. Whatever theory you have to take account of these problems. If the theory is no good, well, invent a new one. But
even though Grishuk has come to Cambridge at the invitation of Hawking's group, to interact with Hawking himself often proves difficult to coordinate.
Hello?
Hello. So hello.
Nice to
Glad to see you again. I wanted to ask you whether Stephen is available and is it possible to talk to him for a while?
He's going off to Spain on Thursday.
Just I wanted to report some of my recent work. I would like to see his face and whether he says yes or no.
Interaction is so important that the British scientists have built it into their tea time. Twice a day, everyone gathers in the interaction room for tea and theory.
So I first computed the horizon size and discovered that it's a plank for perturbations smaller than the horizon size just oscillate, and perturbations which are larger than the horizon size are frozen.
Hello, Stephen.
Yes, hello.
I would like to continue this because it is exactly what I'm doing now.
Yes.
But may I ask Stephen, since I just...
Now you may want to come around here and look at what he's actually saying.
Stricken with Lou Gehrig's disease, muted by a tracheostomy, Hawking can now communicate only through a computer voice box, which he manipulates by squeezing a control instrument.
Between squeezed quantum states and particle creation, and I'm now excited with this.
It sounds interesting.
Right. I'm really excited because, now I am thinking how to maybe even to apply to real observations. And these states must always be squeezed. Even in your process of particle creation in black hole situations, it turns out that they are two mod squeezed states. But it is rather an exceptional case. For instance, for gravitons, I can distinguish gravitons created as a result of
Stephen is among the most inspiring people in the world. He may not be always absolutely right, but on the other hand, everything he suggests something absolutely new perspective, new way of thinking. It is very interesting that this technical difficulty in communicating with him turns out not to be so important.
There is a deep reason for it.
thing in my work. The fact that I love it. The most important is that it gives you enjoyment and it supports you in your life. If you are observing stars, if you are thinking about universe, then some minor difficulties in your life, they are not so important.
And this is the H, and this is done in terms of the frequency of the gravity wave. The frequency response, F is the frequency of the gravity wave. And there's some symbols in this for the delay line, which, and we will talk about for the Fabi Pro as well, which are important. D, the storage time of the light.
So, in my conversation with Brzezinski, when I was in Moscow last August, he described...
The places that Grishuk and Thorne explore in their minds may seem strange and exotic. But so once were the theories of Newton and Einstein.
Interferometry for radio.
Yes.
It is a radio interferometry.
Right. But the dispersion in the plasma is the limiting factor, or one of the major limiting factors. So, a couple of theorists there.
As the boundaries of the universe continue to be stretched, they will open new vistas, new waves to the future.
I think that future of gravity wave astronomy is very bright, because gravitational waves, they have incredible ability to penetrate through depths of matter, space and time, to study the real nature, exploding stars, coalescing stars.
Can you imagine the relic gravitons as being like those sparks of fire coming off?
No, they're absolutely isotropic, so they're not localized.
Some of those are isotropic.
Locally, but you should be surrounded.
I suppose that to some people, dreams of gravitational waves look like medieval theologians musing over how many angels can dance on the head of a pin. But I'm confident those gravitational waves really exist, that they bathe the Earth, that they're passing through me right now. And I am confident that one day the LIGO detector will be shaken by a gravitational wave in a manner we never expected. That its shaking will bring to us a picture of a totally new kind of object, something so new that it creates a revolution in our understanding of the universe.